Hello everyone. Today's topic shall be acid-base balance and interpretation of an ABG. We'll start with the basic acid-base buffer systems and then move on to ABGs. It's not an easy topic, so kindly try to follow.
So what's an acid? So acid is any substance that dissociates in a solution and releases the H plus ion. And what does it do to the pH? It basically lowers the pH. There are a lot of examples. Some common examples are hydrochloric acid, lactic acid, citric acid, carbolic acid. So again, recapitulating, what's an acid? It's a substance that releases hydrogen ion and it lowers the pH. So it causes acidosis. To base is a substance that accepts hydrogen ions to form hydroxide ions in water solutions. And what does it do? It increases the pH. So examples are sodium hydroxide and aluminum hydroxide. So base basically increases the pH.
Coming to one more terminology, pH. So what is pH? pH refers to solution concentration of protons or H+. So what solutions are alkaline? Solutions with less H+ and have pH above 7 and are called alkaline. And those solutions with more H+ have pH less than 7 and are called acidic.
So some basic properties and differences of acids and bases which I've learned during school days. Acids taste sour, bases taste bitter. Acids reacts with metals to give off hydrogen gas. Bases feel slippery. Acids conduct electricity in solution. Bases dissolve fats and oils. And again, regarding the pH of a solution is a measure of hydrogen ion concentration. If you see the diagram below, there is a pH from 0 to 14. So the lower the pH, the more acidic. And see the right side, the more the pH, it's more basic. Here's a graphical representation indicating the relationship between the hydrogen ions and the pH. It has got an inverse reaction. The y-axis shows the H plus ions and the x-axis shows the pH. The grey shaded areas show the normal pH, that is between 7.35 to 7.45. And the numbers above the curve like 10, 13, 17, etc. indicate the increase in H plus with the unit change of pH. So the relationship indicates that 1 unit change in pH corresponds to a 10-fold increase in H plus. So it has got an inverse reaction. So acidosis and alkalosis is a physiological process that lowers or raises the pH. So what is acidemia? It indicates there's a blood pH less than 7.35. So what is increased? The H plus is increased. And what is alkalemia? Means there's a increase in blood pH which is a decrease in H plus concentration. So whenever there is an increase or decrease in pH, our body reacts to it doing certain adjustments through a system called buffer system, okay, which we'll be discussing in the later part of the seminar. Just a graphic representation of alkalosis and acidosis. So alkalosis, the pH goes up, the pH is increased, and you can see the diagram, acidosis means the pH slides down. The pH is decreased.
So, any changes in the pH associated with HCO3 or bicarb is metabolic. It can be acidosis or alkalosis. Acidosis means there is a decrease in bicarb or increase in H+. Alkalosis means there is a decrease in H+ and an increase in bicarb. So there goes metabolic acidosis and alkalosis for you. And the second one, any changes in pH associated with carbon dioxide is called respiratory acidosis or alkalosis. So if CO2 is increased, it's called acidosis. If CO2 is decreased, it's called respiratory alkalosis. So in this slide, revising once again regarding acidosis and alkalosis and metabolic and the respiratory part. So we all know now acidosis means there's a decrease in pH. It's a dictum. And alkalosis means there's an increase in pH. So what the metabolic and the respiratory part has to deal with it? Metabolic always deals with the HCO3 or the bicarbonate. So metabolic acidosis means it's acidosis. So the pH is decreased. Again, it's metabolic part. So the HCO3 is decreased because HCO3 is a base. And metabolic alkalosis means the pH is increased as alkalosis increases the pH and alkalosis also increases the base part. That is HCO3. Now coming to the respiratory always deals with the carbon dioxide. So what is respiratory acidosis? Again, acidosis means there's a decrease in pH. And again acidosis means the acids part is increased. That means CO2 is increased. And coming to respiratory alkalosis, we know it's an alkalosis. So pH is increased. So what happens to CO2? CO2 is decreased because CO2 is the acid part. So that will be decreased.
Before getting into ABGs and the buffer systems, we need to know what is normal. So what is the normal pH in the body? Normal pH is 7.35 to 7.45. What is normal PaCO2, the partial pressure of carbon dioxide in the body? That is between 35 to 45 mmHg. What is PaO2? That's the partial pressure of oxygen in arterial bed. That lies between 80 to 100. What is SaO2? That is oxygen saturation of arterial bed. It is between 93 to 100%. Very important, bicarbonate HCO3. The levels are between 22 to 26 milliequivalents per liter. So these are the values which are going to deal in an ABG, and the main three things we will be talking about and we should be worried about is the pH, the PaCO2 and HCO3, which will play an important role in the assessment of ABGs.
So here's an animation to show you how the pH is maintained and how the acid-base system works in the body. So the pH is maintained at a narrow range between 7.35 to 7.45 in the body, and any changes in the pH can be fatal. You can see now the blue, that's the cells, and the bloodstream, that the cells excrete carbon dioxide that combines with water and forms carbonic acid.
and that carbonic acid dissociates into H plus ions and HCO3 bicarbonate. And all of the components on the left and right side coexist. And the concentration of any component on the left or right will be adjusted accordingly. You can see this diagram. When one side increases, the other side also compensates, increases to decrease the components on both sides and maintain the pH. So whenever there is change in the pH, when there is a deviation from the normal, there are compensatory mechanisms which tightly regulate pH. They comprise of chemical buffers, respiratory regulators, and renal response. They help to maintain the pH. The buffers. So these are compensatory mechanisms, systems in the body which helps to minimize pH. They can either release hydrogen ions or accept hydrogen ions from an acid or a base load. They can act when there is acidosis as well as alkalosis to a certain extent. So buffer pair consists of a base, that is a H plus acceptor, and an acid, H plus donor. So when we have a change in pH, the compensatory mechanisms in our body, as discussed above, the buffer systems, act to prevent the change in the pH. The first to act is the bicarbonate buffer, the protein buffer, and the phosphate buffer, the first line of defense. The second to act is the respiratory system that starts by 2 hours and completes by 12 to 24 hours. And the last to act is the renal system that starts by a few hours and completes by 5 to 7 days. How does the renal system act? It conserves bicarb and excretes H plus ions.
This slide also provides an explanation to the video given above, that whenever there is a low pH, the first scenario, the bicarbonate binds with excess hydrogen forming H2CO, which breaks down into water and carbon dioxide. And when there is a high pH, that is decreased H plus, the carbon dioxide and water combine form H2CO3, which breaks down into bicarbonate and hydrogen ion, and bicarbonate ion is excreted and hydrogen is
So coming to the compensatory mechanisms, when you have an acid-base homeostasis disturbed, when you have acidosis. So as we all know, acidosis means there's a decrease in pH. It stimulates the arterial and brain receptors. So if you have a respiratory acidosis, that means increase in blood PCO2. So respiratory rate is increased. So what happens? The blood CO2 is washed out and blood H2CO3 is decreased. The down equation, H2CO3 can split into HCO3 and H plus. So HCO3 is reabsorbed and H plus is excreted. As we discussed in the first half of the seminar, this equation can be, work both sides to maintain the pH. Coming to the right hand side, when you have alkalosis with an increase in pH, again it stimulates the brain and arterial receptors. So you have a decreased PCO2. So respiratory rate is decreased and blood CO2 is increased and blood H2CO3 is increased. So H2CO3 is a split in the below to H2 and CO2. brief recap of the compensatory mechanisms, and we'll include the renal part too. So, in the disorders, metabolic disorders, we can see the first row, first column, there's acidosis. So, what happens? There's gain of H plus, there is loss of HCO3. So, what happens to the pH in the arterial blood profile? The pH is decreased, as you can see there. The HCO3 is decreased and H plus goes up. Acid goes up. So, what is the respiratory compensation? The baby hyperventilates to decrease the carbon dioxide. And what is the renal compensation? The last column, the kidneys excrete the H plus and conserve HCO3. So in kidneys there is the ammonia buffer and the phosphate buffer, which helps the conservation of HCO3. And coming to the second column, the alkalosis, what happens? There is loss of H plus and gain of HCO3. So what is the arterial blood profile? We know it's an alkalosis, so the pH is increased, the HCO3 is increased, and H plus, that's the acid, is decreased. So what is the respiratory compensation? We know the acid is decreased. So baby shows hypoventilation, respiratory rate is decreased, and there is CO2 is retained. So PaCO2 is increased. And coming to renal compensation, what happens? We have an alkalosis, so HCO3 is increased. So the kidneys excrete the HCO3 and conserve H plus. Some basic principles in acid-base analysis is that pH and PCO2 move in opposite directions. For example, when you have a respiratory acidosis, we have acidosis. That means pH is decreased. And respiratory means it has to deal with the PCO2, carbon dioxide. So that's increased. So what happens? It moves in the opposite directions. And secondly, the pH and HCO3 move the same direction. For example, when there is metabolic acidosis. Acidosis means there's a decrease in pH, and metabolic has to deal with the HCO3. So that's decreased. So they move in the same directions. So regarding the compensation again, it's always going to be opposite. So, just given some graphical representations for simple opposites like dry, wet, and sit and stand. So for metabolic acidosis, the compensation is going to be the opposite. Like the opposite of metabolic is respiratory and acidosis is alkalosis. For metabolic alkalosis, the second one, the opposite of metabolic is respiratory and alkalosis is acidosis. Third, for the respiratory part, respiratory acidosis, the opposite of respiratory is metabolic and acidosis is alkalosis. Fourth, respiratory alkalosis, the compensation is going to be metabolic acidosis.
So this slide is just a recap of the 4 disorders we have learned in the previous slides. So each column you can see, first is the disorder, second is the primary alteration, third is the secondary response, that is the compensation, and fourth, how does the body compensate. So let's have a brief recap. Hope this benefits you. So coming to the first disorder once again, the metabolic acidosis. So what is the primary alteration? We know it's a metabolic, so it has got something to do with the HCO3, and it's an acidosis. So the pH is decreased and the alteration is decrease in plasma bicarb. So what is the secondary response? That is the compensation. We know it's the opposite of metabolic acidosis. That is, opposite of metabolic is respiratory, acidosis is alkalosis. So what does it do? It decreases the plasma CO2. How does it decrease the plasma CO2? What is the mechanism of response? By increasing the respiratory rate or by hyperventilation. Coming to the second disorder, metabolic alkalosis. Again, it's a metabolic, so we know it's HCO3, and alkalosis, so pH is increased. So what is the primary alteration? There's an increase in blood bicarb. So what will be the secondary response? The compensation, the opposite of metabolic alkalosis, that is respiratory acidosis. So what does the respiratory acidosis do? It increases the PCO2. And how does it do? The mechanism of response by hypoventilation or by decreasing the respiratory rate. Coming to the third scenario, that is respiratory acidosis. So respiratory acidosis, what is the primary alteration? It's a respiratory, so it has got some to deal with the PCO2, and acidosis, so pH is decreased. So what is the primary alteration? There is an increase in blood carbon dioxide. And you can see what is secondary response or the compensation for this disorder. How does the body compensate? Opposite of respiratory acidosis, that is metabolic alkalosis. So the plasma bicarb is increased. And how does it respond? How does the body respond? There will be an increase in H plus or acid excretion, and there will be a reabsorption of bicarb, or the bicarb will be retained for this disorder. Coming to the last, there is respiratory alkalosis. So what is the primary mechanism? It's the respiratory, so it has got something to do with the PCO2, and it's an alkalosis. So the pH will be increased. The primary alteration is decreased carbon dioxide. So what is the primary response? Secondary response or the compensation? It is the opposite of respiratory alkalosis. That is, opposite of respiratory is metabolic and alkalosis is acidosis. That is metabolic acidosis. So what happens? There will be an increase in there will be a decrease in plasma bicarbonate, as you can see. And how does it happen? What is the mechanism? There will be a suppression of acid excretion. H plus excretion suppressed, and there will be decrease in reabsorption of bicarb. The bicarb will not be reabsorbed. It will be excreted.
One more terminology, that's base deficit and base excess. By now we know what is the base, that's HCO3. So pH change of 0.15 is equivalent to a base change of 10 milliequivalents per liter. So what is base deficit? A decrease in base, that is HCO3, is termed as base deficit. Normal values are 2. An increase in the base is termed as base excess, that's plus 2. We give bicarb corrections according to these values, also the pH. Now we shall discuss regarding the ABG, how an ideal ABG should be, the technique, the technical errors, and what to look for in the ABG, and how to take an ABG. So an ideal ABG should have a blood gas panel, an electrolyte panel, and it's good to have a lactate, creatinine, and an ABS. So what are the indications of performing an ABG by CBG? Actually, recently most of the units have replaced ABG with CBG. We know the recent machine, this machine has been there for quite some time, for the last 4 years, the Epoch CBG machine. It's better and it's less invasive. We don't have to put an arterial line or we don't have to prick the artery. So, and it gives pretty good results. So what are the indications actually? First indication being the initial evaluation of sick child. If you ventilate a child, to see the adequacy of ventilation, the oxygenation, and the HCO3 and the pH. We get to see after we are ventilated. From maybe we are ventilated after seeing severe respiratory acidosis and distress. So, how is the gas? How is the oxygenation and ventilation after putting the baby on ventilator? And second, it aids in the establishment of a diagnosis, like for the screening of cyanotic congenital heart disease, hypoxia test, and monitoring patient response to treatment. We can actually, it's always good to go clinically, whenever we ventilate a child, when we can reduce the pressures and the FiO2. But with an ABG, we can get a confirmation and monitoring the severity and progression of the disease and to establish a diagnosis. So, before sampling for ABG analysis, we have to select the artery which are going to puncture. If you have an arterial line, like a UIC, it's fair enough. We should always use a stir. If you are planning to prick the radial or ulnar artery, you have to perform Allen's test. Use a 21 gauge needle. You have to flush the syringe and needle with heparin. Enter at 45 degrees. Obtain 2 to 4 ml of blood. If the sample contains air bubbles, push it to the surface. Apply firm pressure at the punctured site. Most of the units now have replaced capillary blood gas. It's easy, less invasive, and less skill is required. And the results are good. What we are going to perform here is the modified Allen's test. It's a video demonstration. So we have to palpate for the ulnar and the radial arteries. The ulnar lies on the medial and the radial on the lateral side of the forearm. Once we palpate for the arteries, we occlude the arteries. Once we occlude the artery, we will see the extremities having blanching as the supply to the extremities is cut off. After 30 seconds, release one side, either ulnar or the radial. If the color returns to normal or the hand becomes pink within 10 to 15 seconds, that indicates there is collaterals. The collaterals between the radial and ulnar artery are well established and intact. And if the color does not return to normal, that means the collaterals are existent. So the ABG should be deferred. So what are the technical errors that occur? When an ABG is taken? The first thing, which is not mentioned in the slide but mentioned previously, the aseptic technique. Second thing, if you flush the syringe with excess heparin, it can cause decreased bicarbonate and PaCO2. Second, if the syringe is filled with air bubbles, it can increase PaO2 and decrease PaCO2. If you have excess bubbles, it's better to discard the sample. If the neonate has fever or hypothermia, pH and PaCO2 can be altered, and ABG normally analyzes report on normal body temperature.
So where to take an ABG? Mostly we do it after UAC insertion or the radial artery or the ulnar artery. But these days, most units have the capillary blood gas, so it's less invasive, it's easy, and less skill is required. So this is the recent blood gas analyzer which has been given for last 45 years. The APOC blood gas analyzer. The advantage is we can also measure the capillary blood gas. So we don't need a invasive arterial line or we don't need to prick the artery. The results are good, and we take the blood in a small test tube and we insert in the card, and the results will be there in about 4 minutes. The machine should be kept in a temperature not exceeding 25 degrees. Most of the people would have seen this apparatus, and most of the NICUs will be having this apparatus. So this is a basic blood gas report. This is a CBG report. You can see the results. First the pH, the PCO2, the PO2, HCO3, the base excess, and the sodium, potassium, calcium, anion gap, chloride, and lactate, glucose, and this is the result from an APOC machine. So it is very important to read each variable and look at the reference variable also if you're not sure what is a normal actually. So this is the way a normal CBG is going to come to you. So we look at the pH, whether it's acidosis or alkalosis. Here the pH is 7.35, it's normal. PCO2 is 45, it's normal is 35 to 45, that's also normal. 3 is 20 to 26, that's also normal.
Finally, the 7 important steps in evaluating ABG bar CBG is a very important. Each steps has its own value. The first step, the clinical scenario. The second, look at the pH, whether it's increased or decreased. That is, whether it's an acidosis or an alkalosis. Who is the culprit? The third step, is it metabolic or respiratory? The fourth step, if it is respiratory, is it acute or chronic? Fifth, if metabolic acidosis, calculate the anion gap. Sixth, is there more than one disorder? Seventh, correlate clinically. We'll discuss each step in detail. Step 1, the clinical anticipation. So, the baby may present with different clinical signs and symptoms. So, each symptom may precede a acid-base abnormality. So, first, vomiting. It can cause metabolic alkalosis, especially newborns with CHPS. We know that it causes metabolic alkalosis. Then diarrhea, it can cause metabolic acidosis. Septicemia and shock can cause lactic acidosis. Pneumonia can cause respiratory acidosis by alkalosis. Renal disorders, we have to think of metabolic acidosis. Pneumonia, bronchial asthma, we have respiratory acidosis and alkalosis. And diabetes mellitus, we have ketoacidosis. Coming to step 2, look at the pH. We have told many times in the seminar, acidosis indicates pH less than 7.35 and alchemic pH is more than 7.45. So if the pH is less than 7.35, definitely it is an acidosis. And if the pH is more than 7.45, it is definitely an alkalosis. So this is one prime step in the evaluation of an ABG. And if the pH is 7.4 or normal, we can have a mixed or a fully compensated disorder, which can be verified by the other parameters. So coming to step 3, we need to know who is the culprit. Is it metabolic or is it respiratory? Metabolic always indicates a change in HCO3 or bicarbonate or the base. The normal HCO3 is 22 to 26, and if it is respiratory, we can always notice a change in PCO2. So the normal CO2 is 35 to 45. The CO2 is the acid. So in the metabolic part, if you have HCO3 more than 26, it's a metabolic alkalosis. And if you have HCO3 less than 22, it's metabolic acidosis. Coming to the respiratory part, if you have PCO2 more than 45, we have a respiratory acidosis. And if you have a PCO2 less than 35, we have a respiratory alkalosis. So step 4, it's a primary respiratory disturbance. We'll see whether it is acute or chronic. So actually changes in pH, the acute changes can be fatal actually, and acid-base disturbances which is chronic can have long-term impact on growth. So in a primary respiratory disturbance, if there is 10 mm change in PaCO2, that can change 0.08 change in pH in acute scenarios. But in chronic cases, it can change the pH to 0.03 for every 10 mm change in PaCO2. And remembering the relation between CO2 and pH, that they move in the opposite direction. So step 5, you have found out that it's a metabolic disorder, metabolic acidosis. So we can find out whether compensation is adequate or not. For that metabolic acidosis, the compensation is going to be, we have learned before, that opposite, that is respiratory alkalosis. So we have a formula for calculating the expected carbon dioxide for that HCO3. That formula is called Winter's formula. So the formula goes by the expected CO2 is 1.5 into HCO3 plus 8 plus or minus 2. And if the PaCO2 is more than the expected value, then there is a respiratory acidosis with the metabolic acidosis. And if the PCO2 is less than the expected value, there is an additional respiratory alkalosis. So this is a continuation from the previous slide. When you have a mixed disorder, so we take a case scenario. We have done an ABG and we have got a HCO3 of 12. So using the previous formula for the expected PCO2, that is 1.5 into HCO3 plus 8 plus or minus 2. So the values derived from this HCO3 is 24 to 28. So when you multiply 1.5 into the derived HCO3 is 12 plus 8 plus or minus 2, we get the value between 24 to 28. And if the PCO2 is less than 24, we have a metabolic acidosis and a respiratory alkalosis. And if PCO2 is more than 28, we have metabolic acidosis plus a respiratory acidosis. Once we have known it's a metabolic acidosis, we have to determine the anion. What is anion gap? The difference between the cations and the anions. Cations are the positive particles, anions are the negative particles. So that is calculated by sodium minus chloride plus HCO3. Normal is 12. So we can, why we calculate this is, we can have a increased anion gap metabolic acidosis, normal anion gap metabolic acidosis. Both have enough significance in the clinical scenarios. So what are the causes of high anion gap metabolic acidosis? Diabetic ketoacidosis, uremia, renal failure, inborn errors of metabolism, lactic acidosis, hyperalbuminemia, late metabolic acidosis of newborn, toxins such as methanol, ethylene glycol, penicillin. Enumerating the causes of normal anion gap metabolic acidosis, such as diarrhea, renal tubular acidosis, hyperaldosteronism, uremia, hypoalbuminemia, lithium, and IgG. And step 7. Is there more than one disorder, like mixed disorders? There are some clues to detecting the mixed disorders, which includes the clinical history, then when pH is normal and abnormal PCO2 and HCO3, when PCO2 and HCO3 move in opposite directions, degree of compensation for the primary disorder is inappropriate. We can find the delta gap if you suspect a mixed disorder, and the acid-base map as Fenley's nomogram.
So finally, the take-home message of this acid-base analysis and ABG interpretation. Point number 1, if you have a low pH, it is acidosis. Point number 2, if you see an ABG and you come across a high pH, it's an alkalosis. Point number 3, metabolic means it deals with HCO3, that is the base. Point number 4, respiratory means it deals with carbon dioxide. And the final point number 5, compensation is always opposite. For metabolic acidosis, the compensation is the opposite of metabolic is respiratory, and acidosis is alkalosis.